Okay, so welcome everyone on a Friday to join the introductory presentation of the open source framework that was developed in the MLSysOps project. So I will be making the introduction. My name is Spiros Lalis. I'm coordinating the project, and the walkthrough and hands-on demo will be driven by Tassos from Nubis and Alexandros from UTH. So very quickly, the project has been funded starting January 23. It will end this December. And it consists of 12 partners, 6 from academia research and 6 from industry all over Europe. You can find more information about the project by visiting the website. We have a newsletter to which you can subscribe, social media, and today's focus will be on the framework, which can be found on the GitHub. So the outline for today, I will make a very short introduction. Hopefully I will not eat up much of the time to explain what the project is all about and to highlight some features of the framework. And then Alex and Tassos will proceed with a hands-on demo. It will start with a setup of what we call a system slice. Then we will install the basic deployment mechanisms, so Karmada Kubernetes, then the MLSysOps framework itself. Then we will see how to deploy an application in the system and how to control its deployment in an adaptive way through what we call policies, which are pluggable, so they can be changed at runtime. And finally, we will make a quick tour in the repo and the documentation that is currently available and which is continuously being improved. All this will be recorded, and at the end, we will stop recording and have a hopefully live Q&A session with you guys. So what is MLSysOps all about? The goals of the project is to support autonomic system management and configuration across the cloud edge IoT continuum. We want to do that for different aspects, including deployment, computing, acceleration, storage, communication, and trust. And the way to do it is through AI ML methods. However, we try to disassociate the mechanisms for these aspects from the control decisions regarding these aspects. And to do that, we have developed a framework. So the main features is that it supports what we call distributed applications, which means applications that are consisting of potentially more than one components in the form of containers in our case, which may also be interacting with each other. We do that through a hierarchical agent-based framework in order to have scalability throughout the continuum. This agent-based framework works hand in hand with standard deployment and telemetry technologies. And it adopts a flexible approach in terms of intelligence through plug-in policies and potentially also machine learning models that can drive some of the decisions taken at some parts of the hierarchy, depending, of course, on the configuration of the slice. These decisions are driven through telemetry that we can support at both the system and application level. Very quickly to show the concept, the bottom shows the notion of the continuum. So these are the resources that are potentially available, and on top of which we want to run applications in a smart way. the parts of these resources that actually consist what we call the slice are captured through a suitable description, and the applications that are to be executed on top of this slice or within this slice across the continuum are also captured through application descriptions. These are fed into the framework, which can handle various aspects, and it decides how to deploy and execute the application. Then we monitor and get telemetry, both at the system and optionally also at the application level. And this is taken into account to adapt the deployment and the configuration of the system. This is done through AI and machine learning, which we aim to be continual, pluggable, meaning that it is not hardwired into the mechanisms that are responsible for configuring all these different aspects, and explaining them. So the framework, it can be thought of as having three main, let's say, pillars. The one pillar is the deployment pillar, which uses off-the-shelf technology, Karmada on top, Kubernetes for the cluster node level. On the other side, we have telemetry. We build the framework to work together with OpenTelemetry, but this is also possible to change if someone wants to do something different. And let's say, intelligence of the framework comes into the form of an agent hierarchy. So we have a continuum agent, cluster agents, one or more agents, depending on how many clusters the slice has, and node agents for the node level. And the way one interacts with the system is through the northbound API. We have also built a command line interface to be able to use the system in a simple way through a terminal. Then at each level within the agents, one can install so-called policies that are used to pick up the telemetry process and take some configuration decisions. And in turn, these policies can be changed at runtime at each level, depending on what one wants to achieve. Plus, from within the policies, we can invoke machine learning models to help with decision making by making predictions or classifications of some patterns, etc. So the idea of today's event is to go through the framework step by step to set up such an instance of the framework as is shown on this slide, and to go step by step to see how to set up the instance from a vanilla, let's say, setup, and gradually set up all the different components, including, of course, the agents, and then to see how an application can be run on top of the system, and how we can also change the policies that guide the application deployment at runtime. So I hope I didn't take too much time, Tasso, Alexandre, so the floor is yours to continue.
Thank you, Spiro. Thanks for the informative introduction. Let me take the share. I hope you can see my screen.
Yes.
Okay, so as Spiros mentioned, the rationale of today's session is to go through all the steps that are needed in order to get a working installation of the MLSysOps open source framework, and of course use it. So deploy an application, see how the policies work, and how we can set and change the way that an application workload is being deployed and executed in such a testbed. So the first step, so we will go, we will walk through the whole installation. So the first step is to provision a testbed where we can install the MLSysOps framework. Essentially, we will deploy a couple of VMs. These VMs are hosted at the moment on an Incus installation. They could be VMs from a cloud provider. They could be VMs set up manually, but it's up to you to see how you want your infrastructure to be set up. A tricky part is that we need to build an inventory for the topology of the testbed installation. So we generate that through a custom script, but this is tailored to our setup. This is, of course, in the repo, and you can use it and change it and do whatever you need to do in your own setup. We feed this inventory to a couple of Ansible recipes that are used to set up all the requirements for the MLSysOps framework to work. So we set up K3s as the local orchestrator framework. We set up Karmada and join the individual K3s clusters into the Karmada control plane. We do that automatically with Ansible, of course. Again, these scripts are in the repo. And using the same inventory, we feed this topology of the infrastructure to the MLSysOps CLI, which is a tool to help provision install the whole framework and manage the whole framework as well. So we will see that Alexandros will walk you through the CLI too. So let's not waste any more time. We will go through the first, the second, and the third steps. I hope you can see the terminal. So at the moment we are on a management VM. So this is completely irrelevant to the setup. We have a script that essentially creates the VMs. So we have annotated with the name of the VMs, the way to generate the inventory. So this is all tooling around the inventory generation, nothing too fancy. So the first step is to create the actual nodes that will be part of the cluster that we will set up MLSysOps on. So this essentially launches the VMs. If we go to the web interface of this system that we use for VM management, we can see that the VMs are provisioned. They start to get IP addresses. So we wait for a couple of seconds to do the inventory generation. In case this fails, we have an extra step to regenerate the inventory in case the IP is not reachable, let's say, by this timeout. So yeah, that's it. So we can just recreate the inventory. We have this inventory file now that describes the topology essentially of the testbed. So we've got the management cluster, which will host the Karmada control plane. We've got the IP address. We've got some keys to be able to log in and manage it. We've got some custom annotations needed for the MLSysOps CLI. We label the nodes accordingly. So given this inventory file, we can start to run. Let me go to we can start to run the Ansible scripts to get the local orchestrator installed and to make these local clusters join the the Karmata control plane. So this shouldn't take more than a minute. So we will just wait for this to finish. However, the Ansible script installation takes about 3.5 minutes. So I will pass the floor to Alexandros to show you a couple of information about the inventory file and the descriptions of the topology.
Okay, thanks, Tassos. So let me take the share. So as
Alex, I think. Yeah, you're probably crashed. Took the share again, so I'm until Alexandros joins again. This is the Karmada installation process. So this will finish by merging all the Kubernetes config files, all the necessary authentication certificates, keys that are needed to control the whole cluster. And of course, it will we will keep the inventory file to be fed to the MLSysOps CLI. Script is running. Let me just check. Okay. Yeah. So Alex, I think you are.
Yeah. Sorry about that. I do the Zoom's crashed. So yes, just let me take the share first. I wanted just before while we're waiting for the installation takes place, I wanted just to make a note that before we install the MLSysOps framework, right now the K3s and Karmada has been installed. So before we install the MLSysOps framework, the system administrator, the system provider, in our case us, needs to build and provide the system descriptions. So system descriptions essentially are YAML files, are custom resource definitions of Kubernetes. And the purpose of those files are to provide to MLSysOps a specific to define explicitly what resources could be managed. Can the MLSysOps framework manage? For example, as we can see here for the node of, for the Karmada node, the description says that you can manage the cluster O1. So imagine in some installations, multiple clusters might be used in the Karmada. So with those files, we essentially define the system define what the MLSysOps framework can manage. Something similar is also on the cluster level that defines which nodes can be managed. But in the node level, it has some extra functionality, and this is to provide some information about the node, about the resources that each node provides, and can also be managed by the MLSysOps. So I will not go in details now. All those are in the description. So those system descriptions are essential and are needed before the MLSysOps installation. In our script, now that Tassos will show, those will be created automatically through the CLI and by using the inventory file. So Tassos, if the installation is ready, please go on with the installation.
Yes, so the installation is ready. So I'm going to copy the inventory file to the Karmada control plane. Apologies for that. So if we log into the Karmada control plane, we see that we have the kube config. So this is a merged kube config of all the available clusters. This is the inventory file. What we need to do essentially to set up. So let me go back to the PowerPoint slide. So we have finished with this step, with the second step. So we're now ready to deploy MLSysOps on the clusters using the MLSysOps CLI. So what we will do is install pip so that we can install the tool. So this is the MLSysOps CLI, a Python tool that we are able to control the whole MLSysOps framework. We are able to install it first, then to deploy an application, to customize the agents, to customize policies. It's a really nifty tool. And it's provided as a Python package. So all you need to do is install Python pip and then do pip install MLSysOps CLI, and you can get this functionality. Let's just wait for this to finish. The requirements for the actual testbed are not high. I mean, these are 2 core VMs with 3 gigs of memory each. So this is we install the MLSysOps CLI with all the requirements as well. We have to make sure that we provide the correct path so that we can access the MLSysOps CLI. There it is. And we also need to set the kubeconfig environment variable, as well as the Karmada host IP, which is, I'm not sure, let me check, 571. Let's do that as well. Okay, and now we're ready to deploy the framework on the cluster. Let me just show you. So this is the Karmada control plane host. So we check the state of the Kubernetes cluster. We only have Karmada system and kube system pods installed, and of course we can also access the child cluster, let's say, which again is a fresh K3s cluster with 1 control plane node and 2 worker nodes. So let me just get the nodes as well. You can see the nodes. And we're now ready to deploy the MLSysOps framework. So we use a deploy all command. The only thing that we need to provide is the inventory file. You get verbose logs. The good thing is that we see ticks, so everything seems to work fine. Alex?
Yeah, I will take it from here. Thanks. So as we're waiting for MLSysOps to be deployed, let me remind you again what we're expecting to see. So we have everything installed respecting Karmada and Kubernetes. So right now MLSysOps framework is being deployed. So we are expecting to see 1 agent per layer. And at the same time, each agent also manages and automatically deploys the corresponding telemetry components, essentially an open telemetry collector. So let's go and take a look. So our clusters are up and running. I hope the view is not too slow. So we are using our own specific namespace, okay? So we can see here the cluster agent and the node agent have been deployed and they are being created. The cluster agent has started just in time. So we also see an open telemetry collector managed by the cluster agent has been started and deployed, and also a Prometheus node exporter collecting system metrics. So if we also open the logs, we can see it started running. And as we can see also in each node, we can see at the node 02 and 03, one set of node, MLSysOps node agent and OpenTelemetry collector have been deployed. So those are on those two levels, okay? And then if we go to the Karmada host, which is in another VM, can go and check if everything has been deployed. So let's check the MLSysOps namespaces. So we can see here the Continuum agent, the main pod. We can also see some other services that are essential for the framework to work, and also we can see the OpenTelemetry collector. So everything seems to have been deployed. So MLSysOps have been installed and it's ready to accept applications. So let's see how we can deploy an application. Of course, first of all, we need an application. In our case, we will demonstrate a simple client-server application where the client sends a message periodically every 2 seconds to the server, a hello world. Okay, so we split the application to two components. So the client is in its own component, and when we say component, we mean containers. So we have one container for the client, one container for the server, and periodically the client connects to the server and sends a messages. At the same time, both components are using the MLSysOps Python telemetry library, and they they send telemetry metrics to the OpenTelemetry collector, so the agents can receive it and can make decisions based on those metrics. So we have two components, and let's see now what we need to deploy those components into the MLSysOps. We need the MLSysOps application description. Essentially, the description is a Kubernetes custom resource definition. So most of the semantics are the same as in the Kubernetes, for example, the container spec. So I will not focus on that. The extra keys that we have in MLSysOps, first of all, is the cluster placement directive. So the application developer can dictate explicitly in which cluster he wants the application to be deployed. So this is how we do it. So in our case, we have a single cluster. So we specifically set it to this cluster, and then we define the components. So the components are, first of all, we define the container spec, and then we can define the node placement. We can explicitly again define where this component should be placed. So the server app will be placed on the O2 node. We will see it later. Whereas the second component, the client app, it has no directive. So the MLSysOps framework, it is free to decide on its own. In our case, it will be a random choice between the two nodes that are available into the system. Another important aspect is the telemetry metrics, the QoS metrics. So essentially, for each component, we defined an application metric that the application component transmits to through the telemetry system, and it defines a specific target and the relation for this target. So all this information is available into the policy that we will see it shortly. So the policy developer, in the policy, we can make decision based on those targets. And of course, there is a global satisfaction, but more details on that, you can find those on the documentation. So we have the application components containerized, we have the application description. So let's go and submit this application. So for this demonstration, we will use a pre-made and essentially it's the same application description. So let me use the CLI to create the description based on the inventory file. So as we can see, if you want a quick look, it is the same, but it uses the node names of the inventory file. So we can now go and deploy it. So we go deploy app, file, path. It was path, I think. Yeah. So application upload successfully. So before going to see what happens, let's take a look on what is the flow. So what happens under the hood when we submit an application description. So we were here. We submitted to the CLI. The continuum agent is the first entity that receives this application description. It decides on where in which cluster should be placed. In our case, it is fixed, so it does nothing essentially. It doesn't do anything smart. It places to the first cluster. So it submits it through the Karmada API, and the Karmada API then forwards the CRD. As I mentioned earlier, the MLSysOps application description is a Kubernetes custom resource. So it is propagated to the cluster level, and then the cluster agent gets this application description and starts making the necessary actions in order to deploy the application. So hopefully, if we go to the cluster level and see the pods, and we change the MLSysOps, the applications are deployed into a separate namespace. So we can see here the cluster agent has deployed the server app placed on the second node as we specifically dictated into the description, and the client app, it has been deployed into a random choice and was the third one. So if we open the logs, we can see both applications running and communicating. So right now we have the MLSysOps framework running, we have an application deployed, and nothing, let's say, interesting happens right now because the cluster agent does not have any active policies. You will see here in the logs there are two core policies that are responsible for the static placement and the random choice, but nothing else happens. So let's go back. How do we introduce the smartness? So let's go back and let me remind you about this policy module. So this is a plugin policy mechanism that essentially we implement Python modules, simple Python modules that implement a specific interface that are loaded into the, in our case, into this level, into the cluster agent, are loaded into the cluster agent and start producing new configuration actions. So let's go and see how this policy looks like. As I said, it's a Python module, and the interface dictates that three methods are needed. So the first one is the initialize. The initialize method is essentially a way for the policy developer to ask for some configuration options, for some configuration that are needed from the policy. One important thing, for example, is the telemetry. As we said, the telemetry, if you opt in to use the Open Telemetry Collector and the MLSysOps framework managed telemetry system, the policy can ask for specific metrics to be collected from the node system and how often, how the interval of this collection. The policy also can ask for Python packages to be installed at runtime. So you can import any Python package and you can use it and it will be installed at runtime. And also there is some custom variables that can be used from the policy developer. So the initialize function is essentially a way of communicating, of configuring the agent to work seamlessly with the policy. Then we have the two major methods, the analyze and plan. As it was mentioned in the introduction, the MLSysOps agents work on the MAPE paradigm, so in the monitor, analyze, plan, and execute task. So the monitor task is constantly running under the hood, inside the agent, collecting data, telemetry, whatever is needed. So it can be exposed in the policies. And then we come to the analyze and plan. So essentially, those methods implement the analyze and plan logic of this loop. I will not go into details on each argument. You can see those on the documentation, but we can mention the application description, which is essentially the application description which submitted and built it earlier. So all the information in this application description is exposed here. So the application, the policy logic can access for example, the telemetry metrics and the targets. And also in the system description is the system description we mentioned here. So for example, as we will see, we can access which nodes are available in the system. And then we also have the telemetry that it essentially is an argument that exposes the telemetry metrics that are collected. So for the analyze function, we will use two examples. Before that, I talked about the arguments. So what about the output? What it returns? What it is expected? The returning value is a Boolean value, a true or false. And the idea behind this is that it must decide if we need a new plan or not. So if it is true, we need a new plan, and then the plan method that we will see later will be called. Otherwise, if no new plan is needed, it returns false. And the context is just for storage of persistent value to persist values between different calls of analyze. So this analyze essentially runs periodically. That can be configured by this analyze interval. So in order to decide in the first example, to come back in the examples that I mentioned, the first example essentially returns true every 30 seconds, every moving interval seconds. So as we will apply, when we will apply this policy, we will see every 30 seconds the client component to move between two nodes. So this is a very trivial logic, and we will see it in action shortly. So when this analyze returns true, as I mentioned, a new plan must be produced, or it should be produced. So we come here into the plan method. As we can see here, the plan method gets information from many different entities from different arguments. So, for example, it gets information from the application description to see which components are in this description. It gets the state of the placement mechanism. The mechanism is the module that is responsible for deploying the components. So this new plan, what it does is it finds in which node is currently placed the specific component, the client component, where it is placed. And it also finds another candidate node that we will relocate this component. So it finds a node to place the component and builds a specific payload with the plan, the instruction that move this specific component from this host to that host. And it returns this new plan to mechanism in order to take action. So with no more detail, let's go see it in action. So I have installed the MLS CLI here. So we have a specific command set. So we need to set policy to the cluster agent, this policy. It has been deployed, and first of all, let me show you that each policy essentially is a config map. It's a simple configuration map for the agents. So we can see it here. It has been applied. this was empty before, and then it has been applied. And then if we go to the pods to see the effect of it, as you can see here, maybe make it, let me disable those. As you can see here, the restart, the age of the client app component is 23 seconds. So it has been relocated. It's in the node 02. And if we go in the logs of the cluster agent, probably somewhere, we can see here the relocate components policy. It has been added and it runs every 5 seconds. And as we can see here, every 30 seconds, it moves it between the two nodes. Now it's in the third node. So let's prepare a more smart policy. First of all, let me delete this policy. So as we delete it, and if we, as I told you earlier, and go to the config maps, then we will see that it is empty. So let's see the second example. Let's use some telemetry to make decisions, because this was a very simple. Let's uncomment those. So in this example, in the second example, we use information from the application description. So in this line, we get the target, the quality of service target. If let me go back to this, we get this target that has been defined into the application description, and we also get the measured metric, the latest metric that was received by the client component, and then we run a comparison. So essentially, what does this count? It counts how many messages the client has sent. So every 30 messages that has been sent from the client, it triggers a relocation. So let's go and set again the policy. Okay, perfect. So we can see here the analyze has the new logic. And let's go to the pods and to see it in action. So let the namespace. So in here, we can also here in some, I hope they are not too small, we can see the telemetry that is received from the application components. So we need some time for it to trigger in order for the policy to be loaded and trigger its logic. So imagine if in this policy we have the application description information, we have the system description information, we have telemetry. So you can imagine on all the possibilities on what you can build, what logic, what policy you can use and build using ML or not. So let's see if it has been loaded. Yep, it triggered just now. So the new policy has been loaded, as we can see. So a new plan was produced. So those are the logs. A new plan has been produced and has relocated the component based purely on the telemetry metrics. And I think with that, I finish my presentation. Hopefully everything worked. So Tassos, please, the floor is yours to finish.
Thank you, Alex. Let me take the share. So what Alex has shown essentially is the core mechanisms of the MLSysOps framework. Of course, this is as we mentioned it as the title of this session says. This is an open source framework, so everything is on GitHub. We welcome contributions from everyone. So let me. I have a couple of screenshots here. Let me actually go to the repo to show you, walk you through a bit around it. So it's a standard GitHub repo. We try to follow all the standard practices around an open source project. So we have a code of conduct, we have a contributing document, proper license, we have a short brief README on what the framework is, what the repository contents are, the prerequisites, a really, really short quick start as we showed. We have documentation embedded in the repo. So this gets built based on markdown files that are available in the repo. So this is work in progress. This is under heavy construction. We try to capture all the aspects of the framework in this documentation website. So from the rationale and the architecture to hands-on installation instructions, the testbed setup, quick start, which includes not only what we showed, but other ways to deploy the MLSysOps framework on custom infrastructure. I mean, it doesn't have to be Incus, could be VMs provisioned with a Terraform approach or something else. We've got the design and architecture section where we describe the rationale of the framework. Again, let me just stress that this is work in progress. So we haven't finalized the documentation. And of course, as an open source project available to the public, we have gathered some basic issues that people can work on and contribute. The label is good first issue, that without having any knowledge about the framework, you can contribute. The way to contribute is essentially do a fork of the repo, make a branch with your fix and issue a pull request. We have tried to enhance and have essentially a linting linked workflows as part of the of pull requests. So your contribution will be spell checked and checked against the proper license or the proper commit messages. We have a contributing document that it's again work in progress. And we also have a roadmap, which is of course work in progress. We plan to have a release in September, a follow-up release in September. Our first release was in June, and another release towards January that coincides with the review of the project. Our plan is not to stop developing this framework after the project ends, because it's an entity of its own. We think it's a useful software component, so it's something that hopefully will be useful to other people as well. Let me go back to the presentation. Yeah, as I mentioned, the documentation is under construction, heavy construction, I would say. And with this, I think we can wrap up. The key takeaways from this session, I think it's that we try to provide, we have built this framework to provide mechanisms in order to manage workloads across the whole continuum in a pure cloud native way. We have introduced smart agents that coordinate and take care of efficient resource utilization in the infrastructure, that are able to add smartness to workload placement, to relocation, to whatever you think is meaningful regarding the actual execution of the application. And this is just the first step. Everything is accessible using the MLSysOps CLI, this tool that we introduced. So you just can install the MLSysOps CLI and then manage the whole application and framework lifecycle through the CLI. And as I mentioned, this is just the first step. The MLSysOps framework is a lot more than what we've shown in this session. We have other components that we plan on showing on a follow-up session. So there's the ML connector, how ML blends in the whole framework. There's also the mechanism plugin, which is similar to the policy plugin, but can provide more functionality to how workloads are being executed and deployed in the framework. We've got support for far-edge devices, fine-grained support for application execution like sandbox runtimes, or adding hardware acceleration functionality to workloads. As I mentioned, the current release is 0.112, which is essentially, it was out in June, end of June. We have a planned release for 0.2 in September, with all the developments done since June, and the roadmap, as I mentioned, on GitHub. I think we're done in terms of what we had to say. Feel free to ask any questions. The process is you can raise your hand, and we click on a button to ask to unmute, and then you can unmute and you can say whatever you want. Maybe we could stop recording and have an open session, whatever you guys prefer. Or you can push your question to the chat, and we can respond with more information.
So I think we should stop recording and then take questions. I think that's the